Porg 1 material, can you draw 4 resonance structures for the following compounds? With the oxygen off of the double bond, we know all we can do is send the electrons up to the oxygen to form a negative and a positive on the benzoic carbon, and then just chase the positive around the ring till we get the right number of resonance structures. And this one we can draw 6. Okay, normally I only ask for 4 in a resonance structure, but we'll draw all of them just to get them all in. Send it back in from the oxygen. We reform the carbonyl and get the 3 double bonds in the ring. Okay, and remember, when you draw resonance structures, the one I gave you does not count as one of the 4 or 6 that you have to draw because I gave it to you. I don't give points for the stuff I draw. Okay, in aniline, we can't send electrons out to the nitrogen because it already has 8. All we can do is send them into the ring. So we send them into the ring and we get a double bond to the nitrogen. And then 4 electrons at a time, we can send them around the ring. I didn't use the iPad very well on this one. And then send it back to the nitrogen. And we get that. Okay, so those are the 2 resonance structures. This one is an electron donating group because you have the electrons on the atom right off of the ring. The only thing they can do is go into the ring. This one is an electron withdrawing group because you have that double bond to the more electronegative atom off of the benzoic carbon. So the electrons go out to it, and then you have a positive charge that you can resonate around the ring. Remember your resonance structures, they're on every test, and we're getting into aromatics where everything depends on the resonance structures you can draw. Okay, here we are starting electrophilic aromatic substitution reactions in the aromatic chapter in general. And we've said before this video that you never do anything to the aromatic ring itself. All you do is the stuff off of the aromatic ring. Now we can finally get into doing a reaction on the ring itself, and we have electrophilic aromatic substitutions, and we have a few nucleophilic aromatic substitution reactions. So those are really the only things we can do. So in this, in an electrophilic aromatic substitution, we have to come up with, shockingly enough, an electrophile. So we need to come up with something with a positive charge on it for the aromatic ring to attack, to add on to it. So when you look at all of these things, that add on to the aromatic ring, we have to get a positive charge on it. The SO3 is different in that it has 3 double bonds, 2 oxygens, more electronegative oxygen, so it doesn't have a full positive on the sulfur, but it has a big partial positive charge. And then the cation on the carbonyl or the cation on the carbon. So we have to come up with these electrophiles to add to it, and there aren't a lot of options in what we can do, so we have to make sure we follow along with the rules of organic chemistry. And the 2 main ones we need to worry about: electronegativity and resonance. Okay, and those 2 primarily will get us through most of what we talk about in this chapter and in every chapter in organic. So what's the mechanism look like in an electrophilic aromatic substitution? We have the aromatic ring is the nucleophile. It goes and attacks the electrophile, whatever the electrophile is, the thing with the positive charge. Okay, it goes on the aromatic ring itself, and yes, we can draw resonance structures moving the positive charge in the ring, around the ring. and then we can use some base, something we have in solution, to remove the hydrogen to reform aromaticity. So in electrophilic aromatic substitution reactions, one, you start with an aromatic ring, you end with an aromatic ring. We do not get rid of the ring itself. We do not decompose the ring, make it just an alkene or anything. We have that aromatic ring in the end. And in this, we're doing a substitution where whatever the electrophile is substituted on the ring, and we put it on and then take off a hydrogen. Okay, so make sure you remember in this, it is a substitution reaction. We have to be careful where we draw the positive charge, because when the bond breaks to go attack the electrophile, the carbon next to the carbon that the electrophile added onto ends up with a positive because it has an empty orbital when that pi bond broke. Okay, and we'll draw a lot of mechanisms and a lot of resonance structures as we go along in this chapter. So there are two ways we can see about drawing the electrophilic aromatic substitution reaction with the halogenation. Okay, and depending on where you see it, you may see it either way. Neither way is right or wrong. Either way is fine. Okay, so we can have the bond between the two bromines break, attack the iron bromide. That gives us the full Br plus, and then the FeBr4 minus, and then the bromide could be kicked off of that to reform the neutral iron bromide, where it grabs the hydrogen carbon bond breaks, going down to reform the aromatic ring. Okay, that's where the bond between the two bromines breaks and goes. If we want to have just a lone pair on one of the bromines go attack the iron bromide, we form this complex with the bromine with a positive, the iron with a negative, and then the aromatic ring itself can go attack a bromine, kick off that good leaving group now to form the bromine on the aromatic ring with a positive charge on the adjacent carbon, and just like above, then the bromine on the iron can be kicked off with its electrons going to grab the hydrogen to give us the bromobenzene. So we can draw it either way. I don't care which way you draw it. Just be careful that you keep all the arrows correct in the way you draw it. So the sulfonation reaction is neat in that we can put on the SO3H, and then with dilute sulfuric acid we can take it off, so it can be used as a blocking reagent for this. Now the mechanism for this, shockingly enough, is just like the mechanism we just showed. Okay, so and then we can go the opposite way with sulfuric acid, and we'll draw that later. The reagents for the nitration are shown below, where we have nitric acid and sulfuric acid. We all know that nitric acid looks like this: positive on the nitrogen, negative on one oxygen, and then your sulfuric acid. So the electrophile here, we have to form NO2 plus. So we have to get a nitrogen with a positive charge, two double bonded oxygens. Okay, so we have to get to that electrophile to have the aromatic ring attack it and get to the nitrobenzene. Once we've added the nitrobenzene, we can reduce it with iron and HCl, and we can make aniline. So this is nitrobenzene, and this is aniline. And we talked about nomenclature on in the last chapter, chapter 16 of this section. So we've already talked about those things. And that the aromatic ring goes and attacks the sulfur. We get a positive charge on the adjacent carbon, and then some base comes in and grabs the hydrogen to reform the aromatic ring. And the base that does this is going to be another one of these sulfate on another oxygen on another one of these. It's going to come grab the hydrogen off. So really you have two of these around, where this comes and grabs the hydrogen. So you end up with the sulfonic acid, and then one of these, which it would then go grab a hydrogen off of another one. So you keep grabbing the hydrogens off of the aromatic rings to get the sulfonic acid. So we can do the Friedel-Crafts alkylation or the Friedel-Crafts acylation. In the alkylation, we have to get to an alkyl cation. So we have to, our electrophile in this one is going to be positive charge on the aromatic ring. The pi bond attacks it, forming the cation in the ring, and then your chloride is going to come in and take off the extra hydrogen. The ones that do not react, okay, are the vinyl chloride and the aryl chloride. Those do not react because you cannot form the carbocation. Okay, so remember those. They're good reactions that you may see as a, not necessarily a trick question, but just to see if you're thinking about what can go on in that, is can you really form the cation. Okay, and the next one has a small error in what I drew. Okay, I need to change that. But if you have a withdrawing group on the ring, you cannot do the electrophilic aromatic substitution with Friedel-Crafts alkylation or acylation. It gives no reaction because we have the electron withdrawing group on the ring. So we have to be careful anytime we have an electron withdrawing group, and we know what the electron withdrawing groups are. We've talked about them. Hey, we know electron donating group is an aromatic ring with some group off of it that has a lone pair on the benzoic atom. Okay, the atom right off the ring, it doesn't have to be a carbon, it could be an oxygen, a nitrogen, whatever, has either a lone pair or it has a lot of electrons off there. The one example that doesn't have a lone pair is if you have like a T-butyl group. We learned a long time ago that an alkyl group is an electron donating group. It's electron rich. We can't draw resonance structures, but the carbons are electron rich. Carbon chain is electron rich, so it is also a donating group. Okay, so the donating groups all have this group off of the ring with a lone pair on it. Okay, anytime you see that, it's going to be a donating group. The other possibility is the electron withdrawing group, and for the electron withdrawing group, as we have said in the past, it is a group off of the aromatic ring that has a pi bond to a more electronegative atom. So in this one, the XY, the Y has a partial negative, the X has a partial positive. The one of these that's different than this is if you have a full positive on the atom right off of the ring, that's also a withdrawing group, even if you can't draw resonance structures to it. So with the electron withdrawing group, we'll either have a positive right off of on the atom right off of the ring, or it'll have a pi bond to a more electronegative atom. Then we have the Friedel-Crafts acylation, where we put on what's known as an acyl group, a carbonyl, and so we have to form the carbonyl with a carbon with a positive charge, and then that we can reduce with zinc, mercury, and HCl to make the alkane. Okay, so activating groups versus withdrawing groups. If we have an activating group, okay, toluene, we said alkyl groups are donating groups. So this is a donating group, so it's going to react at the carbons that are, if we could draw resonance structures, would have a partial negative or in full negative on them. Okay, they're the carbons that are more reactive because of we're pushing electron density into the ring. Okay, with toluene, we can't draw any resonance structures moving electron density into the ring because we don't have any free electrons off of it, but we know that methyl is electron rich, so we can put the main products are going to be the ortho and para substituted nitrotoluenes. Okay, the meta-nitrotoluene is way down on the list in the amount we form because we have that donating group on there. The ring is electron rich, either ortho or para to the donating group. Okay. So the nitration of anisole, can you draw resonance structures for anisole? We send electron density into the ring. We get the negative on the ortho carbon. We can send it around the ring, put a negative on the para carbon. Still have a positive up there. We can send the negative back up to the ortho carbon. And then we can send the lone pair back out to the oxygen. So in this, where is the ring most nucleophilic? It's nucleophilic at the carbons where we can draw a negative charge in the resonance structures. So that's going to be, we can put a negative here, we do here, we can put a negative here, and we can put a negative here. So we can put a negative charge on these three carbons, the ones with the little red dots. So when we have a donating group, those are the places we will put a group on. Okay, when we have the donating group, the primary products are going to be the ortho and para products because of resonance work when we put the negative charge, when we draw the resonance structures. And you can all draw the resonance structure showing this. So deactivating groups, electron withdrawing groups, nitrobenzene. Can you draw the resonance structure for nitrobenzene? We have to send the electron density out to the oxygen. So we get a double bond, two single bond, oxygens with negatives, positive on that nitrogen, positive on this carbon, and then just chase the positive charge around the ring. And then send the electrons back in from the nitro. It doesn't matter which oxygen you send them in from, either one. So in this one, we are putting a positive charge in the ring. We're putting it on the ortho and para carbon. So those three carbons end up with a positive charge when we draw resonance structures. And remember, in this mechanism, the ring is a nucleophile. So where's the ring going to be most nucleophilic? Not where we can put a positive charge on it. So the ring is going to act as a nucleophile at the carbon where you can't put a positive charge on it because it's more electron rich where it doesn't have a positive charge. So a withdrawing group, our product is the meta substituted compound because it's not going to go from the ortho and para positions because that's where we put a positive charge. So we've talked about donating groups and withdrawing groups. Withdrawing groups are deactivators, donating groups are activators as a whole, and activator and deactivator is just what it sounds like. An activator speeds up the reaction, a deactivator is going to slow it down. The one exception to all of this is halogens. Halogen has the lone pairs on the atom right off of the ring, so from what we said earlier, it would be a donating group, or an ortho-para director in a donating group, but halogens are not activators, they're actually a mild deactivator. Okay, and this comes partially from the electron withdrawing group of the electronegativity of the group off of the ring, even though it has the lone pairs on the ring. So chlorobenzene is a donating group. It is going to react ortho and para. It is a deactivator, so it's going to be a slower reaction than some of the others. So we have all of the electron donating groups, the ortho para directors. We have the strong activators. They're the things with a lone pair that doesn't have any resonance pulling it away from it. So an OH, an O minus, an NH2, and any of the amines. They're strong activating groups. Moderate activators are the esters and the amides, or an ether in that, because the ether and the ester and the amide, the ester and the amide, we can draw a resonance structure sending some of the electron density towards the carbonyl. So they're moderate activators. The weak activators are the alkyl groups off of the ring, because we can't draw any resonance structure sending the electron density into the ring, but we know the alkyl group is a donating group. And then the weak deactivators that are OP directors are the halogens. So these will react very fast, much faster than as we go down. Each step along the way, it'll get to a slower and slower reaction because we have a weaker activating group on there. So then we have the withdrawing groups, the deactivators, and the moderate deactivators are the carbonyls, the pi bonds to a more electronegative atom, but without the strong withdrawing group of having a full positive on the carbon, like the nitro, because we can draw it out. We know the nitro has a positive on the nitrogen and a negative on one of the oxygens, so it's a strong deactivator or a positive charge on the nitrogen. Okay, we have a strong deactivator on those also, and these are all meta directors. So we drew earlier the mechanism. Had the bromine split apart to go add to the iron bromide, forming the electrophile. The aromatic ring attacks that electrophile, and then one of the bromines comes off to form the double bond, grab the hydrogen and reform the double bond of the aromaticity. So the mechanism always looks like this for electrophilic aromatic substitution reactions every time. Okay, if you can draw once, you can draw it 100 times. You can draw for any of the reactions I ask. They're all this mechanism. I can't get sneaky in what I ask. This is it. So you have to just be able to figure out how is it going to go on the ring. And in the first one, we know this is an electron donating group, and we have drawn resonance structures for it where we put a negative charge, ortho and para, to the methoxy group. So because of that, it's going to react ortho and para to that, because that's where we put the negative charge when we drew the resonance structures. And you should be able to draw a resonance structure, or 4 resonance structures for anisole, to show where the negative charge is. You should also be able to draw 4 resonance structures for acetophenone and show where the positive charge is in the ring. Electron withdrawing group. To show where the positive charge is in the ring, and the carbon that it's going to react at is the carbon that doesn't have the positive charge. So it is a meta director when you have an electron withdrawing group off of the ring. If you have multiple substituents, the directing effect is going to be based on what is the best donating group on the ring, because the donating group, the best activator, controls the reaction. Okay. And then the second thing is steric effects. If you have a big bulky isopropyl, the major product is going to be want to be where we add the group as far away from that as possible. So the ortho one would be the minor product, the para one would be the major product. Okay. If we have a couple of alkyl groups on there, we have these 3 spots as somewhere we can put something on. The one that's going to be the major product is going to be the one that has the least steric hindrance, and then the other 2 are right next to the isopropyl. So the minor one would be the one with the isopropyl only on one side, and then this one would be very, very small amount, if at all, where the nitro goes between the isopropyl and the methyl. So blocking groups, if we needed to block a carbon, we could put a blocking group on there if we didn't want it to react in a certain spot. Okay. If we wanted to form the 1,2 substituted t-butylbenzene, add bromine onto the ortho position, we would need to block the para position so the bromine didn't add there. So we'd take the t-butylbenzene, install the blocking group, brominate it. It would go ortho to the t-butyl, and then remove the blocking group. And the only blocking group we have is the sulfonate, because we can put it on and remove it. So with fuming sulfuric acid, we can put it on. With dilute sulfuric acid, we can take it off. So the SO3H group is a perfect group to put on so that we can put it on, use it, and then take it off when we don't want it there. So we could install the blocking group with fuming sulfuric acid, brominate with bromine and iron bromide, so here's the reaction sequence again drawn out. So we fuming sulfuric acid, put it on, brominated, then dilute sulfuric acid, take it off, and we have the desired product. So we have to be careful. What are we trying to make in the different reactions? How can we go about doing it? And thinking about how they can react together. So what can we do to an aromatic ring? Okay. And I know first thought you're thinking, oh, all these reactions are all different. No, they're all the first set of arrows from the acetophenone over here on the right to bromobenzene on the left. The mechanism to form all of those is exactly the same. You form an electrophile, the aromatic ring attacks the electrophile, and then you remove the extra hydrogen. Then what can you do with those? The nitrobenzene we can turn into aniline by reducing the nitro group. The sulfonate, we can remove it to go back to benzene, so it's that good blocking group. The methyl, we can brominate with bromine and light, or we can turn into the carboxylic acid with hot KMNO4. And the ketone, we can reduce down to the alkane. Okay, so or we could reduce it to the alcohol if we needed to have more variety in what we could do. Okay, so there's a lot of things we can do. Most of these are reactions we've covered in the past. A couple of them are new, of the side reactions, but they're all things that, remember what you're trying to do. Are you trying to reduce something? If you're trying to reduce something, you need to have a reducing agent around so there won't be any oxygens in it, because the oxygen isn't in a reducing agent. Oxygen's in an oxidizing agent. So be careful what you write down. Is it really the right type of thing for what you're trying to do? So for an aromatic ring, we can turn a nitrobenzene, a metadirector, into aniline, an OP director, by zinc and HCl. We can turn the metadirector acetophenone into an ortho-paradirector, reducing the carbonyl down to the alkane with zinc, HCl, zinc, mercury, and HCl. We can turn toluene, an OP director, into a metadirector by overbrominating the carbon with making CBr3 off of it. Or we can take an OP director of toluene or any alkane and make the carboxylic acid by oxidizing it with KMNO4 or sodium hydroxide and heat, followed by acid to protonate the OH. So these types of reactions, what we're doing is we're changing it from one type of directing group to another in each of these, either metadirector turning into an OP director or an OP director turning into a metadirector. So remember your resonance structures. There's a reason why I've been bugging you about them since the day you walked into Org 1. Keep thinking about resonance structures and what they mean to you. So one of the things we have to be careful of is reactions that will not work based on what we have. If we take aniline and try to nitrate aniline directly, we cannot nitrate it, because the only way to nitrate something is with nitric acid and sulfuric acid. Okay, aniline is a weak base, so if we add it to acid, we're going to form the anilinium ion, positive charge on the nitrogen, and it is now a metadirector. So it wouldn't form the orthopara, or the para-substituted product. It'd form and then down here at the bottom, oh, I forgot my double bonds. Down here at the bottom are two other reactions that we said earlier wouldn't react, but a Friedel-Crafts with an electron withdrawing group on it will not react because the ring's not a good enough nucleophile. The ring has to be a good nucleophile to do a Friedel-Crafts acylation or alkylation. So any withdrawing group will kill those. Okay, so far we have done electrophilic aromatic substitution reactions. Here we have nucleophilic aromatic substitution. So it's still a substitution reaction, but instead of substituting for a hydrogen, we are replacing a leaving group that is on the ring with primarily an alcohol. We're making a phenol. So in this, we need a strong base, high temperature, and then followed up with a little acid to protonate the O-. Okay, so in this, the OH adds to the aromatic ring, send the electrons around the ring. Oops, drew that arrow poorly. Send the electrons out onto the nitro group, and then we can send the electrons all the way, and we could have drawn that all the way at once, all the way back through. So we end up with the OH on there, then we're in base. We have to do what everybody doesn't like, take the hydrogen off to form the phenoxide, and then put the hydrogen back on, because this is resonance stabilized, and we get to the product. Okay, So in the middle of the mechanism we formed the product, we have to take the hydrogen off to put it back on. And in this reaction only works because we have this strong electron withdrawing group on the ring that we can resonate the electrons all the way through when the hydroxide adds, and then send them back through, kicking off the leaving group. So if you don't have a strong withdrawing group on there, nothing will happen either. And it has to be ortho or para to the leaving group on the ring. So if the strong withdrawing group is meta, it's no reaction because we cannot send the electrons from the hydroxide. If it adds in, we can't get it to go out on the nitro, period. So it's no reaction. Okay. Now, in the book, it'll says it's possible to replace the chlorine on an aromatic ring if you do hydroxide and heat it to 350 degrees in a sealed tube. Just say no reaction. That is not a way we can put an OH on. We're not heating some chlorobenzene and hydroxide to 350 degrees in a sealed tube and making something that will be high pressured and could explode. No. We like safety. So just think of that as no reaction. If you do this reaction on a test, I will write -5 on it or whatever it's worth, because this is not a way we can do things that's useful. Okay. The chlorine can be replaced with sodium amide and ammonia, where it comes in, attacks a hydrogen, forms a triple bond, and then adds back in. So it's an elimination followed by an addition. Okay, we can do this, and when we do this, we get the nitrogen adding to either side next to the carbon, either the carbon that was the chlorine or the carbon that was next to it. Because of what happens, NH2 minus in the mechanism. Okay, so if we had a radio-labeled benzene with the chlorine carbon, we see that we get two possible products with the aniline, the nitrogen on the carbon with the radio label or next to it. So the only way we can think about this happening is have the NH2 minus come in, form the negative charge on the ring. The ring negative charge could form a triple bond, kicking out the chloride, so you get the triple bond within the ring, and then the NH2 minus could add to either carbon to give us both of the substituted anilines. The benzyne can also be trapped with a Diels-Alder reaction. As we have shown in the past, a Diels-Alder needs a dienophile and a diene in the cis configuration. So this right here would just give us this. Okay, if we had just ethylene. If we have the triple bond there, it's going to react with the furan, and it's going to form a bicyclic system where in the end we would have the aromatic ring off of the bicyclic system. Okay, so we'd still have the aromatic ring, we'd still have the carbons of the furan. We've just formed that six-membered ring in between the two. So how can we draw the mechanisms? An electrophilic aromatic substitution, we've drawn it many times. The aromatic ring attacks the electrophile. You can draw the resonance structures and then take off the hydrogen to get back to the aromatic ring. So it's nucleophilic attack and then the proton transfer. In the nucleophilic aromatic substitution, it's nucleophilic attack, a bunch of resonance, and then a loss of a leaving group. Okay, and we can draw these both very easily as we're going along, and make sure you know the difference between nucleophilic aromatic substitution and electrophilic aromatic substitution. And then we have the elimination addition reactions where we go through the benzyne intermediate. So we need to be careful. What do we have as possible to what can happen? So to decide between the possible mechanisms, do we have an electrophile or a nucleophile? If you have an electrophile, it is an EAS mechanism. If you have a nucleophile, it is either an NAS or an elimination addition reaction. Okay, and for there to be a nucleophilic aromatic substitution reactions, you have to have a strong withdrawing group on ortho and para to the leaving group. If no strong withdrawing group, choices are elimination addition or no reaction. Okay, and no reaction is a possibility with these, so be careful about that. So here we have the 5 electrophiles that we will work with on this section. Can we form the electrophile? So the bond breaks, we form Br+. Here we need to protonate the nitric acid to make a leaving group, and then reform and kick out the leaving group, and we have that. Okay, and when this happens, we get the positive on the nitrogen because we have 2 double bonds. Then the next one, the Friedel-Crafts acylation, the bond between the carbon and the chlorine can break, go into the aluminum, giving us the acyl cation. Fuming sulfuric acid, if you have to show it forming, would be just like what we showed earlier. So we protonate the oxygen of the sulfuric acid, much like we did above. Messed up my pen. Okay, and that gives us an OH2OS with a plus on there, and then the single bonded OH can kick off that good leaving group to give us this, the SO3 H+, and then our water could take that hydrogen off to give us just the SO3, or we could have the aromatic ring attack that. Either way would be fine, and that gets us there. And then the last one, we know we can't have a primary cation, so the chlorine leaves, the hydrogen migrates over, all at the same time to give us the isopropyl cation. Okay, so those are the 5 mechanisms for this section. They're the only thing we can do. Be careful about that. Know these mechanisms and what happens with them, and the test will be good. So here we have predict the products for the following reactions. We have a donating group in the first one, so we have to draw 2 products, the ortho and the para, disubstituted brominated compound. The next one's a withdrawing group, so it's going to give 1 product, bromine meta 2. The next one is an OP director, so 2 products, nitroanisole, and of the ortho and para, nitroanisole. Then the next one is 1, 2, 3, 4. Got an extra carbon on there. Sorry. Makes the ketone 2 products. You have to show them both. Ortho and para. The next one has a strong donating group on, so we'll go ortho and para to it, so we'll get 2 products. The methoxy rules that the ketone doesn't matter. In the next one, the methoxy rules, we get 1 product next to it, not next to the carbonyl. I forgot my aromatic ring up there. And then the last one And then in the last one, we have the withdrawing group. So it's going to be a meta director, NR3 plus, and then the SO3H on the other side. Okay, so you just have to get good at identifying withdrawing groups versus donating groups. Okay, so here we have a synthetic scheme. We are missing the aluminum chloride here, but the methoxy is a better donating group than the bromine, so we're going to put the group on there with the bromine, and then nitric and sulfuric acid is going to nitrate. The methoxy is the best donating group, so our nitro will go there with the bromine. Zinc and HCl reduces the carbonyl, so we're going to make the alkane chain with the bromine and no nitro. HBr cleaves the ether. It's going to give us methyl bromide and the phenol. KMNO4 is going to completely cleave the alkyl chain off, giving us the carboxylic acid. Bromine and light is going to brominate the benzoic position. So we'll have the two bromines on our ether. The azide ion here is going to do an SN2 on the only bromine that's on an sp3 hybridized carbon. So it's going to give us the N3 there. The methoxy, an argument could be made for either the substitution or the elimination, since it's a strong base. Then we have the Birch reduction with the donating groups on, so they're going to be like that. The next one is going to make the isopropyl, because you'll have the rearrangement. The bottom one here, we have the electron withdrawing group of the carboxylic acid, so we'd get that for our Birch reduction. And then the mechanisms, nitric and sulfuric acid, draw it that way, HOSOH. So we grab a hydrogen off of the sulfuric acid, kick out the leaving group to form the electrophile, use the aromatic ring to attack the electrophile, which gives us the OMe double bond, single bond, nitro with a hydrogen, and then with a plus, and then our base, our water, would come in and grab the hydrogen and send the electrons through to get to our product of that. N3, just an SN2. This is that bromine. And then HBr, cleavage of the ether, you protonate. We'll just draw the aromatic ring, the rest of it doesn't matter, and then the bromide adds to the methyl, send the electrons down. You get the methyl bromide along with the phenol. Then the next page, starting with benzene, outline a synthesis of propyl benzene and isopropyl benzene. The isopropyl benzene is easy because we can just use the Friedel-Crafts alkylation and do it directly and make the isopropyl benzene. The other one, the propyl benzene, we cannot do that easy. The first step, we have to do the acylation to make the ketone, reduce the ketone with zinc, mercury, and HCl, and then we have propyl benzene. This is the only way we can make the straight chain. We can't do it any other way. Don't do it any other way. It's wrong if you do it any other way. Okay, we have to put the ketone on there and then reduce it to make a straight chain group. Phenol is more acidic because the conjugate base of phenol, the phenoxide, is stable because you can draw all the resonance structures for it. Acidity, this is 1, this is 2, this is 3 because of resonance. This one's 4, this one's 5, this one's the least because this is the donating group, the methyl group. Okay, predict the products. If we add hydroxide to a phenol, we're going to take the hydrogen off because hydroxide's a base, phenol's an acid, and then we're going to make the ethyl ether in an SN2. We're going to make phenol and ethyl bromide with that. Okay, now we haven't done this next mechanism yet, but we will. So aniline and NaNO2 and H2SO4 makes the phenyl azide, and then whatever's on the copper replaces that. And this is the only way we can make phenol, is go from aniline to the diazonium salt and then replace it with the oxygen. Okay, so don't do it any other way. On the next one, we can do this. We'll draw the mechanism for this one in class when I have more space. It's just an electrophilic aromatic substitution. Electrophilic aromatic substitution, you're adding a CO2, which is just like adding SO3 on there. Nucleophilic aromatic substitution, where we have the strong withdrawing group. Make the diazonium salt, replace it with what's on the copper. So, and then this is no reaction. And then the last one here is draw a mechanism. Send the electrons all the way through out onto the nitro. And then send the electrons all the way back, kick out the chloride to get the alcohol with the nitro. Oops. And then our hydroxide takes off the hydrogen to get the phenoxide. And then we protonate it with acid. And we get the product. Okay, so here is chapter 17. Hey, if you have questions about any of these, when we're going through it in class, ask, send me an email, however you want to do it. I'm here to help you. Okay. Have a great day. I'll see you in a few minutes in class.